For most of our history, exoplanets existed only as statistical dots on a spreadsheet. We assumed they were slight, unimaginative variations of the planets we already knew, expected to follow the same patterns we see in our own solar system. Then we found HD 189733b. It orbits a small orange star in the constellation Vulpecula. Its name is a catalog number rather than a poem, and its location is so unremarkable that you would need a star chart just to pick it out. But the environment on this world is a direct challenge to our imagination. The air is hot enough to melt lead, and the rain falling through the sky is composed of tiny shards of molten glass. To understand the mechanics of the universe, we cannot only study worlds that look like our own. We have to observe what happens when standard physical laws, the same ones that govern Earth, are pushed to their absolute breaking point. HD 189733b forces us to abandon our Earth-centric view. It proves that the universe operates at scales and intensities that make our own neighborhood look like a quiet exception. The violence of this world begins with its orbit. It hangs against its star at a distance of about 4.5 million kilometers, roughly 30 times closer than Mercury sets to our own sun. On this planet, a full year lasts just 2 days and 4 hours. This extreme proximity causes tidal locking. The planet is gravitationally forced to keep one face staring at its star forever. One hemisphere is trapped in permanent burning daylight, while the other remains in a perpetual simmering twilight. The resulting temperature gap is immense. The dayside is locked at over 900 degrees Celsius, while the nightside, though shielded from the star, still glows at 650 degrees. Even the cool half of this world would melt aluminum on contact. In 2007, the Spitzer Space Telescope mapped these temperatures and found something unexpected. The hottest point on the planet wasn't directly under the star at high noon. It was shifted to the east, proving that the atmosphere refuses to let that heat stay in one place. The atmosphere equalizes the heat with a planetary jet stream moving at 8,700 kilometers per hour. This is a supersonic wind system that scoops up the heat from the dayside and drags it across the terminator line into the dark. By simply moving a planet this close to a star, the laws of physics weaponizes the air. Basic heat disparity is transformed into an unstoppable global gale louder than anything our own atmosphere could produce. This environment changes the very nature of the materials within it. Consider what happens to ordinary silicates, the minerals that make up sand, when they are subjected to these temperatures. On the scorching dayside, these minerals vaporize into a gas and rise into the upper atmosphere. The supersonic winds carry that vapor toward the nightside, where the lower temperatures cause the silicate to condense back into molten droplets. In 2013, the Hubble Space Telescope measured the light reflected by the planet and found it was deep cobalt blue. While Earth's blue comes from oceans, this planet's color comes from clouds of suspended silicate glass scattering light. Because of the 8,700 km/h winds, these glass droplets never have the chance to fall straight down. They are flung sideways, tearing across the sky in glowing horizontal sheets of liquid glass. In 2024, the James Webb Space Telescope detected a new molecule in this atmosphere, hydrogen sulfide. To a human observer, this world would have the unmistakable pungent stench of rotten eggs. Sulfur serves as a tracer for planetary formation. Unlike lighter elements, sulfur-bearing compounds only condense and integrate into a growing gas giant in regions cold enough for ice grains to trap them. This chemical signature proves the planet wasn't born in its current position. It formed in the freezing suburbs of its solar system, where those sulfur-bearing ices could exist, before a violent migration dragged it inward towards its star. The blast-raining environment we see today is the chaotic result of that millions of years-long journey from the cold outer dark to the inner fire. Astronomers have dedicated 20 years to studying this single, unreachable world 63 light-years away. It raises the question of why a place that will never affect us deserves such focus. The reason is that HD 189733b operates on the exact same physics we have on Earth. It is a laboratory for what happens when you take the equations for gravity and heat and run them at the highest possible settings. This world has become the foundational test case for modern astronomy. Every new technique, from mapping alien weather to measuring the chemical fingerprints of distant air, is tried here first to see if our models hold up against reality. We focus on the glass rain because it is spectacular, but the discovery is the work of decades. It is the result of researchers cross-checking data at 3 in the morning and tracking tiny discrepancies in light beams that left their star before the personal computer was even invented. The universe is not waiting for our permission to be interesting. It has been operating this way for billions of years. Our role is simply to be patient enough to look up and notice how the light describes these distant realities. If the idea of sideways glass rain made you stop and think, tell me which part of this world's history was the most surprising in the comments. Subscribe to see more deep dives into these extremes. And if you know someone who would lose their mind over a cobalt blue glass world, send them the link.